All right. So I did not have you guys read anything ahead of time because it was fall break or Christmas break for it. So we are starting into Module 8, but you haven't read ahead unless you have. That's great. So we're going to go over where we've been and where we're headed and why it matters. And then we're going to stop and do our first experiments because it's always fun to do labs. So we're going to do our lab today, 8.1. And if we have any extra time, we'll watch one of the videos as well and kind of talk about where we're headed. So Module 8 is all about energy. And I know initially you kind of stop and say, Ms. Thomas, we already learned about energy. We know that energy is measured in joules, and you know that because it was on your semester final, right? Because we already learned about it. So one of the things that we get to see in life, and especially in science, is that things are consistent. And why do we have consistent things? Well, because we believe that they are created with an order, and that God created it with an order. And since God is orderly and not full of chaos, then our world is orderly and not full of chaos. So what we're getting to see is that the same things that we explored in our first semester on an atomic level, a molecular level, where we're looking at the very unseen things, they work together exactly the same as in our seen world because there's consistency. And that's what's great about it. It's like, if this is true at our very, base level in atoms, it's also going to be true out in the regular world. So a couple of things is, initially when we started this whole science thing, we started at the very beginning, right? Everything is made up of an atom, and we learned all of the different parts of it and how it all works together, and we have elements and mixtures, and they work together, and there's different reactions that were based upon how many protons, neutrons, electrons, all of that, So we learned all of that structure, and we also learned that we could make observations that something was happening. So the two different ways we made observations were qualitative, right? Qualitative means
like the quality physical thing about it, just, no, that's the opposite.
Yeah.
Color.
Perfect. So our five senses. Yeah, qualities about it. Taste, smell, color, touch, those things. And then we had quantitative. Quantitative means it's got a number sign, hashtag, numbers before it was a hashtag, right? The number sign. So we have two of them, or there's 11 students in this class. So we get to take those from both the base level and then move it forward because as we have been learning, we get to make decisions on is something moving or not, right? We had to have a reference point. We had to use our senses. We could decide how far it had moved. So same things, we're just expanding our scope, okay? We also learned about mass and volume. We learned that there was mass and volume within the atomic structure, how many protons and neutrons make it up. You've got your atomic mass. And then we have mass of items, right? Everything has mass. Weight depends on what?
Gravity.
Gravity. So your mass doesn't change, but your weight might, depending if you're here or Mars, right? So we also learned that mass in the atomic level determines an identity of something. And when we were learning about force, force is dependent upon the mass, right? So our mass carries over. These are important things that we're learning about. Volume can tell us a lot about the state of matter. If volume is packed really close, we usually have a solid. If volume is spread out, we're going to have a liquid. If volume has more room to work, you're going to have a gas. So we worked through all those, and then we decided that we are going to look at how everything moves. And we had the bonds, and that's where we brought in some energy, right? So the bonds were the chemical makeup. It's whether or not it's held. We had ionic bonds. Remember, ionic bonds are more like what?
Magnets.
Magnets, right? Because one thing was positive and one thing was negative, and they're attracted and they're staying together just because we've got polar opposites, right? And they're attracting. Or we had them where they were joined and they were actually sharing all those electrons, which was called what kind of bond? Covalent. Excellent. So we had those different things, and how they were bonded together determined if it was a solid, liquid, or gas. It determined how it reacted. It determined how the energy was used, because if we have an ionic bond, the energy to break that bond was less than if we had a covalent bond, right? So if it's tied together, it's going to have more energy that you're going to have to break it apart. So again, we've got that energy pulled back in, okay? And then we also learned that energy is measured in joules, okay? So then we had a whole chapter that talked about moving, and we learned about our favorite superhero, Vector, right? And he is a change in both magnitude and direction. But if something is moving, we have to have energy to move it, right? If you have not eaten breakfast, you don't have a ton of energy to go to a track meet or do a tournament, right? So the amount of energy that we have and our bodies have determines how much movement we're allowed to do. In the same way, the amount of energy that's in an element or in a bond determines how much movement it's allowed to have, right? So when our electrons went from really far outside circles and they dropped down a whole bunch, they released a whole lot of energy. And in those situations, we learned it could have a whole lot of reactions, right? Because it's moving a lot. So our movement can go in different ways. We can have displacement. We have 3 different types with movement. Displacement is dependent upon the starting point, right? So you started this morning in your bed. Tonight you will end up back in your bed. Your displacement is 0. Now, there was a lot of movement that happened, but your displacement was 0. We then had our vector, which is magnitude and direction. So that's, I'm going to walk from here to that door. And so I have a distance that I walked, and I'm going to say it would be northeast, that I'm headed that direction. Or we had a scalar and just said, I ran 5 miles today. You could have ran 5 miles in a square, so your displacement is still 0. Or you could have ran 5 miles and 4 was a square, and then you ran over to Ben's house, and so your displacement is 1. Whatever it looks like. So we got to learn how to work all of that together with our movement. Then we talked about how does movement affect anything, okay? And that's when we started looking at the distance that we moved and relating it to something else. So we took everything we learned about movement and we said, what if we measure this movement in relation to time? So once we added and we combined our movement with time, we got speed, right? So we learned about our distance time graph. We learned that distance equals rate times time, or speed times time. So now we have speed. So we learned something else. All we did was take an ad and said, hey, what if we talk about our movement in relation to time? Then we had speed, and we said, what if we talk about our speed in relation to time? There's 2 different types of speed. I think I have it up there. We have instantaneous speed, and we have our average speed, right? So if I'm driving from here to Tulsa, instantaneous speed is, I'm looking at my speedometer and I'm reading what it says. Average speed would be the total distance that we traveled and the total time that we traveled. So sometimes I might be going 80, sometimes I might be going 65. Sometimes I might be stopped in traffic. So we had 2 different options that we had for speed. And so then when we take our speed and we look at speed over time, we've got acceleration. Now, can you have acceleration and have your instantaneous speed the same at any point?
No.
Can you have constant speed and still have acceleration. That
yes,
was a special
if
term.
you're turning.
Yes, if you're turning. So often we looked at it and said, if our speed doesn't change, we have no acceleration. If I'm just going 50 miles an hour straight, I have 0 acceleration. However, acceleration is always dependent upon direction. I wrote speed for there. Acceleration is dependent upon direction because we've got, with speed, we had to have a direction because it's magnitude and direction. It's that vector format. And so it matters if I'm going north or south, right? So if we have a change in direction, so something that's maybe turning in a circle or you're spinning it over your head, it's going the same speed, but the direction is changing, we have constant acceleration in that form. Right? Does that all make sense? How all we've been doing is just working through? Okay, so then in our last module, right before we left on break, we took all that information, everything we knew about speed, everything that we knew about velocity and acceleration, and we started looking at forces at work, right? Because there's lots of different forces that are always working. We learned about several. We learned about gravity. We learned about friction. We have 2 different types of friction. Who can tell me the 2 different types? Static and kinetic. Okay. That's important to learn because as we move into energy, we have the same thing. Static meant nothing is moving yet. Kinetic meant it's already moving, right? So as we move in today, we're going to have potential energy, nothing is moving yet, and kinetic, something's already moving. Same thing. We've got consistency through there. Okay? So we had our different types of friction, and then we had applied friction. So we can push on, or applied force. We could push on something. We could pull on something. We're going to apply forces with it. We learned an important, where's my thing? We learned an important thing about forces. Our total force was all of our forces combined, right? So we might have something with a frictional force. We might have an applied force. We might have 2 or 3 different applied forces. And we're going to look at our total force, and that's going to determine that movement that we've got, right? All forces follow 3 rules. Our Newton's 3 laws. Law of inertia. Why did we call it the law of inertia? Who else can explain something for the first law of Newton?
Is it object in motion stays in motion?
Or an object at
Stop.
rest stays at rest. Yep. So inertia, the word inertia meant resistance to change, meaning it wants to stay in the same state that it was in. If I'm laying down on the couch, I want to stay laying on the couch. If I'm running in a half marathon, I'm probably going to just keep running until I get to the end. So we want to keep doing what we were doing. So inertia is the desire to do what you were doing in the first place, right? Our second one has to do with force, okay? Force is dependent upon the mass and the acceleration. So again, we've brought that mass back into it. It matters. How much we have of something is going to determine how much force we have. And then for the third one, we had our equal and opposite reaction. So every reaction, or every action has an equal and an opposite reaction. Pushing on one thing, something else is pushing back on it. And then the only time that you actually have movement is if those forces are unbalanced, right? So as long as it all balances out, and we had the nice example where the guys were pushing on each other's hands and kept walking their feet out and there wasn't any movement, as long as everything is balanced, we have no motion, okay? But as soon as something in the system changes, then the whole system has to change. When one part changes, every other part of that changes. And so that's what we're going to then walk through for chapter 8 as we look at energy. So we have to understand where things are changing. The important thing that we learned way back when we talked about energy, what's the one important rule about energy? Energy is never
Created or destroyed.
Excellent, Gavin. Energy is never created or destroyed. So when it says God spoke into being, everything that ever was going to be and ever has been was created at that moment. Nothing, no new stuff has been made, no old stuff is made. We are simply changing forms. Same for all the matter. If you think about water, I could sit here, I could boil it. As long as I can contain it in a container, it'd be the same amount of water that would turn into water vapor. And then I could stick it all in liquid nitrogen and it would turn it all into a solid. It would be the same amount of matter in that. It's just changed forms. We haven't lost any. It's just changed forms. So that's the same thing for energy. It's not created or destroyed, but it can change forms. Okay. So for Module 8, again, we know that atoms, where does this energy come from? So if its energy is not created and it's not destroyed, if we're now seeing motion and we're seeing new energy, where does it start with in the first place? We're going to rewind back to energy is found where? Where is energy stored?
Chemical bonds.
In the chemical bonds, in the bonds of an atom. So the energy exists already. So we've got to be moving and breaking those bonds to release that energy and have the energy, okay? So energy increases as matter expands. Again, something that's solid and stuck together, it doesn't have a lot of movement. So if we're tying energy with movement, the less movement we have, probably the less energy we have. Gases are going to have a lot more energy. And energy, I wrote, is the fundamental building block of motion and change. Without energy, nothing changes. Without energy, no motion happens, right? Because you have to apply something to create that unbalanced force, right? Because if the forces are unbalanced, nothing changes. There's no change for that, okay? So energy is defined as the ability to do work, move, or change matter in some way. A lot of times it's the ability to do work or to create heat. Remember when we were doing our equations and we were saying it produces heat, or it produces light, or it produces sound? Those were the keys that we knew energy had been released in that way, okay? So when work is done on something, energy is then transferred to it by a force. So if I'm going, I won't throw it. If I was going to throw this cap, if I just think I need this cap to be thrown at Luke and him to catch it, is this cap going to move? No. A force has to be applied. So the energy that is in my body has to move to the cap to give the cap energy to go through space, to resist the air pressure, and then when the cap is caught, the energy that's in the cap is now transferred to the hand that's catching it. So I've now transferred energy from myself to Luke if he catches this cap. The energy didn't disappear, didn't go anywhere. It's just transferred. It's moved places, okay? Okay, so what is energy? Energy is the ability to do work or heat up objects. In the same big picture, I like this slide. It shows graphically that there's lots of different types of energy. And that's kind of what we've been figuring out in this whole science thing, right? We talk about here's our big picture, and then we break it down into a whole lot of different things. I think we did that in Module 2, where we had the slideshow, and it was like, man, these are the 18 different things we've learned along the way. So we're going to look at big picture of energy, and then we're going to start breaking it down into all the little parts of it. This is what we're going to start looking at today. Initially, we're going to start at the top. Next week, we're going to look at the bottom parts, okay? So just as I was talking about that you have stuff that moves and stuff that hasn't moved yet, right? We've got the same for energy. Energy, we've got kinetic energy, energy that's moving, the same as kinetic forces, right? Kinetic friction. Isn't it nice that they're using that same word in it? Kinesiology, the study of motion. So we've got our kinetic energy, and then we have our static energy. Means it's not moving yet. We had our static friction, and so static energy is called potential energy. It means it's stored. It's there. It's just not being used yet, the potential. And a lot of times in life we hear, hey, are you living up to your potential? Or there's the potential to do something. It means it's in there. It just hasn't been expressed yet. So those are the two different parts that we're going to look at today for kinetic and potential energy. Okay? So we're going to start with movement first, and then we'll look at not moving things. So kinetic energy is energy of motion. There's a special formula, and it says the energy depends upon the mass and its speed. Okay? So we've had a couple different things because force depends on mass. So it seems like a lot of things are depending upon mass. Mass also determined, if we go all the way back to the elements, mass determines what the element makes us up, correct? With protons and atomic mass. So yeah, mass is important. It's going to determine how things move, how things react, where they go, how much force they get to apply. So we've got mass and speed. A thing that's interesting is, do you remember when we had that 1/2 gravity times speed squared? If we were looking at the distance that something fell, or not speed, time. So on your test you had an apple is dropped. It took it 3 seconds to fall. How tall is the tree? Or how tall are you at? So it's interesting to me that it's set up almost exactly the same. That we have 1/2, a constant, and then another variable squared. And we've got 1/2 mass, velocity squared on it. I think God has a sense of humor in that often. So when we are looking at kinetic energy, that energy of motion, we've got 1/2 times the mass, however much it weighs, times however fast it's going, squared. Okay, so if our mass increases, what's going to happen to our kinetic energy? Kinetic energy is on one side of the equal sign, and mass is on the other side of the equal sign. They're both in the numerator. This is called a direct relationship. In the same way, if I had x equals 2y, so if y goes up, x goes up. If y is 1, x is 2. If y is 2, x is 4. Direct relationships when they are on opposite sides of the equal sign. So if my mass increases, my kinetic energy is going to increase. Okay? So if I double my mass, I'm going to double my kinetic energy. Now let's look at speed. Speed is squared. It's also on opposite sides of the equal sign. They are both in the numerator, so it's also a direct relationship. But there's something special about this one because it's squared. So if I double my speed, I don't double my kinetic energy. If I double my speed, it's squared. What happens to my kinetic energy? What's 2 squared? 4. Okay. So if I double my speed, my kinetic energy increases 4-fold. This is called an exponential increase. So what this tells us, if I want my kinetic energy, if I need more energy out of a system, I can either increase the mass that's applied to the system, and it will increase my energy, or if I just change how fast my system is going, I'm going to cause a lot more kinetic energy change. Okay? This works with bicycles. Who's ever had a 10-speed bicycle? Or a bicycle that changes speeds? Okay, you have different speeds because you have different gears. Okay? The gears determine how fast your wheel is going because the chain is going around with your mass being the same, or you could even push harder on it and that's going to increase it. But if I change gears and I go from a larger gear to a smaller gear so that in that distance it's making that wheel go twice as fast, I am now getting 4 times the amount of power and energy out of my bicycle with the same amount of pushing, simply because I'm making it go faster. So I could stay on the same gear and just push harder, right? Apply my own change to the mass that's pushing on that pedal, or I can change gears, make my wheel go faster, and have an exponential change. So this is how in real life it works and plays out. Okay? And then kinetic energy is always transferred. So transferred when it's moving from one object to another, and we ask why. That goes back to our energy is never created or destroyed. So if I have something in motion and it hits something else in motion, or it hits something else, it will transfer energy. Now, whether or not that new object experiences motion is dependent upon all those other forces at work on the other object. Okay? I love to play pool. That's probably mine. I love to play pool. Anyone else like to play pool? Okay. So, you break, I'm not doing very good on my thing, okay? So I'm hitting my cue ball, and it is going, whatever force I have on this cue ball, the energy applied here is going to be transferred to all of the other balls. So the balls that absorb the most energy are going to move the most, right? The balls back here at the back, probably not going to move the most because we've got energy transfer, energy. So I've got them out here. If I spread it out equally, at the very least, I've got some balls on here that are going to have at least half the amount of energy that got started up front. So we're just transferring it out. Right? So let's consider, okay, let's look at this one. A car and a bicycle are traveling at the same speed. Which has the most kinetic energy? Kinetic energy is dependent upon mass and speed. So, the car is because
It's heavier, it has more mass.
it has more mass. Excellent. Okay? So if a ball weighs 1 kilogram and is traveling at 20 meters per second, what is its kinetic energy? We're going to take our kinetic energy and say we've got 1/2. What is our mass? 1 kilogram. Now, it is important that we are working in kilograms because remember, joules is our energy, and joules is kilograms per meters per second squared. So I need to have my mass in kilograms, and I need to have my speed in meters per second squared. If we don't have these, we need to use our conversion factors to get them, right? It says 20 meters per second squared. So what is my kinetic energy? 1 times 1 times 20? 20. 2 times 1? 2. 20 divided by 2? 10. 10 joules is my energy. Oh, sorry, 1/2. Sorry, that was kilograms. I forgot to square it. You're right. I forgot to square it. Which is 400. 400 divided by 2. 200. There we go. Okay, 200 joules. All right, so I had a couple of interesting facts about kinetic energy. You guys can look that up if you look at your slides again. Okay, so then let's look about potential energy. Okay, so if we know that kinetic energy is all the stuff of motion, potential energy means it's not moving yet. It has the ability to, but it's not yet. Okay, so potential energy becomes kinetic energy the moment it starts moving. In the same way that static friction becomes kinetic friction the moment it starts moving. They don't coexist. It's either one or the other. All right? Okay, so potential energy is dependent upon position. That's important to know. I always just kept the P's together, potential and position. Okay, so it's a height in relationship to something as well. So that goes back to when we were looking at displacement. Displacement mattered, right? So in the same way, potential energy matters. So if I'm doing it in relation to the floor or to the ground, the potential energy of the cap to drop is 1 here. If I raise it, my potential energy has increased. If I am on the 2nd story of a building and I move to the 3rd story of the building, my potential energy has increased in relation to the amount that I moved, not in relation to the ground. So there's different ways. Potential matters, like that reference point. So that's why it was important to look at that reference point for motion. Remember, it's like, who's moving? Well, it depends on the reference point for it, okay? So potential energy is mass times gravity times height. You can do MGH. When I was college, we did it as MAH, M-A-H. Mass times the acceleration of gravity times height. Whatever you can use to help you memorize it is fine with. So again, these are all direct relationships. They're all on the opposite sides of an equal sign. They're all in the numerator. So if mass increases, energy increases. Is gravity going to change? Not unless you change planets, right? So this is constant. If height increases, energy is going to increase. So our potential energy is dependent upon both the mass and the height. If one goes up, the other goes up. If one goes down, the other one goes down. Okay? It's also measured in joules. We know that potential energy, as far as like dropping something in relation to the ground, works. Potential energy also is elastic. So springs, rubber bands, guitar strings make motion. So anything that can be stretched and has to return to a location, or a spring can be compressed, but it wants to return back to its original position, can all hold potential energy in it. And we'll watch that at the end of class. Nope, I don't want to watch it right now. There we go. Okay, so let's look at this. We're going to solve these and we're going to go to lab, okay? So it says, what is the potential energy of a 2 kilogram rock sitting at the top of a 10 meter cliff? So I've got a 2 kilogram rock up here at the top of a 10 meter cliff. My potential energy, my mass has to be in kilograms. Do I have kilograms? Yeah, so I've got 2 kilograms. What is